Hey, Mary, thank you for watching this video. So here is the demonstration video I made this evening to show you how to calculate, first how to delineate drainage area for any given location with the DM data, digital elevation model data, and then calculate the percentage of each type of land use land cover data within each drainage area. So that's just the general introduction. Let's get started. So first, I want to stay up front. What is my starting point and what will be my deliverables? So as you can see, our final deliverable desired product will be a table summarizing the percentage of all area of each type of land cover within each watershed. And my starting point include the water boundary shapefile, which represents the boundary of the Shivers Creek. In this video, this shapefile is not used in the actual GIS operation processing, but rather being used as a reference layer so that I know where I am. And then second, input data is a land cover data. And the Shivers Creek boundary and land cover data both were downloaded from the CZO website. To be fully disclosed, the land cover data, according to the CZO website, the resolution is 30 meters, which is not very high. So if you're, you know better than me about your drainage area. If your drainage area is very small, you may want to use a higher resolution, like a 5 meter, 1 meter or something, even better. Another input data I used in this video is DEM, the digital elevation model data. DEM data I used is 3 meter resolution. I downloaded it from the Penn State TASDA website. It has tons of DEM data, so you can check it out. Oh yeah, so before I do the delineation, watershed delineation, I cropped the raw DEM data I downloaded just so that I can only keep a subset of the raw DEM data so that I can save time in all of those subsequent operations processing steps. Another input data I got, oh, by the way, for the DEM data, if you are working with a very small drainage area, if you expect your drainage area be small, you may want to use a higher resolution DEM data. For example, 1 meter or even below 1 meter. Another input file I have been used in this video is sampling location list. That's the CSV file I got from you. So that's my starting point. Cool, let's get started. So so here is the interface of my ArcGIS Pro. If you use Pro, you should see similar interface. If you use GIS ArcMap, you may see something different. But functions, all of those functions I'm gonna show you, probably you can find it easily in the ArcMap. So on the left-hand side, it shows you all the map layers. For example, the samples 18N, samples 17N, you probably can guess by name. So that is just the 2 groups of samples in the list of sample locations you sent me. And each of them represent 1 location group. As you can see, if I check it, it will show up. So that represents the group of sample in the zone 18, and then the other layer represent all the sample in 17N. In this video, I'm gonna only work on the 17N sample just to give you an idea how to do that. You can easily apply the same knowledge on 18N. So before we actually get started, I want to show you at a high level what will be the steps. So our final goal is get a table summarizing the percentage of all area of each type of land cover within each watershed. So to reach that point, we need to start from the loading data into ArcGIS Pro, which we have done. And then we need to fill DM. So these steps, basically, we process the DM to fix some minor issue in the raw DM data. And the process the DM data will be used in the next step to calculate the flow direction, just to show what direction the stream flow will run towards. And then next steps, we will use the flow direction data to create the flow accumulation data. I will explain in details what we do with flow direction and the flow accumulation, why we need it. And next steps, sometimes, which is actually optional, sometimes if your sample location is perfectly located on the river stream, then yeah, that's fine. You don't need to do the snapping, but for whatever reason, if there is a minor discrepancy between your recorded sample location and the actual stream, if there's a discrepancy, you may need to do the snapping or even manual editing. And the next steps is the actual steps of delineating drainage area or delineating watersheds for each given sampling location. Okay, let's get started. So again, on the left-hand side, you see I have a bunch of layers. So the blue one is the boundary of the Shepherd's Creek, and the black polygon represent the boundary of the Pennsylvania County. The Shepherd's Creek, as you know, is in Huntington. And then next data layer is the DM. That's the cropped one. It's not a raw one, so I reduced the size of the data to save time. And then next data is a land cover. As you can see, it's color coded. Okay, let's get started. On the right-hand side, I mean, in my ArcGIS Pro, my geoprocessing toolbox is on the panel is on the right-hand side. You may different spots, but you should have same panel. And in the geoprocessing, we need to click the toolboxes and then go to the spatial analyst tools. And then under the hydrology, you'll see a bunch of functions we will use in following maybe 10 to 20 minutes. So first, we are gonna start with the fill function. Double click it. So as I mentioned earlier, fill function, we use it to fix some minor issue in the raw DM data. Okay, it takes some time to load. Okay, so it's loaded. The input surface raster should be the raw DM, so that's the DM data. And then the output, you just give it the name. I usually name it fill_DM, or you can give it a longer name with the region name, something like that. I will just click run. It may take like 30 or 40 seconds on my computer. Depending on the capacity of your computer, it may take longer or shorter time. So let's wait for a while. Okay, it's almost done. Cool. So it's done. On the left-hand side, you see a raster data layer named fill_dm showed up. As you can see, when you compare the data of fill dm with the raw dm, you see the minimum and maximum. They're slightly different as expected, but not that different. Okay, so then we fixed some minor issue in the raw dm. Then we can go to next step, which is we can calculate the flow direction, and the input surface raster should be the field dm, and then give it a name of the output flow direction data. So I usually name it flow_dir. Just click run. I expect this step should be faster. Let's see. I could be wrong. Cool. So you see the layer of flow direction shows up on the left-hand side contents panel, and they are color coded. Each number represents a direction. So it could be east, west. You can look up. You can Google it. What each number which direction does each number represent? And then next steps, we're gonna calculate accumulation. So accumulation will be the steps, will be the output to show you where the stream or where the river bed might be located. So the input should be the flow direction we just got, and then the output, we need to give it a name. I usually just name it flow_ACC. Let's see. Okay, just keep it default here, and click run. This step may take a while. Cool. It's down. So in general, it's like almost all black, but that's not true. And then we can change the symbology to highlight the string. So if you right click on the flow accumulation, and click the symbology, and then change stretch from classify and change it only 2 classes, and change the color scheme to black and white, and change the upper units of the black category, change it to okay, my computer freezes. Just 1 moment. Okay, 2, and then change it to manual, and then change the upper value, change the value to 5,000. So basically, what it means any cell to which less than 5,000 cells flow into will be treated as non-string cell. Let me rephrase that. So all the black area which represent the cell value smaller than 5,000, that means as long as the cell has less than 5,000 area, which in map unit, which has less than 5,000 contributing cells, that cell will be treated as non-string cell. If that cell value is larger than 5,000, it will be treated as a string cell. So we can zoom in. So each red dot represents one sample location that you send me. So the white curve represents the potential string flow line. So what we need to check by zoom in is we need to see if those sampling points are located on the string. So we need to check all of them. So these 2 are on the string. Okay, this one also located on the string, which is good. And this one also on the string. So there are 11 points. For demonstration purpose, I'm not gonna run the check. I'm not gonna check all of those 11 points, but you get my point. You need to check one by one, and that's the time-consuming part. So what if you have a sample that is not located on the string? If it's not a lot of samples, if it's not a lot of sample points, you can manually move that sample point to the nearest possible string line based on your field knowledge. So you can Google online how to edit the location of a shapefile point. That should be very easy. So, okay. So up to this point, what do we got? We have fixed the raw DM and the field DM, and then we calculate the flow direction, then we calculate the flow accumulation. So up to this point, we can start to do the actual watershed delineation steps. So we should go back to the geoprocessing panel. Then you see there's a function named watershed. Click on it. Then you need to use the flow direction we just created, and then input the raster of features. So which should be the sample 17N or the corrected sample 17N. So which means if you have some sample not located on the flow accumulation, the white flow, the string line, you have to fix it. And then if so, here you need to use the fixed sample location layer. And then the pool point fill, which will be the fill you use to label the output drainage area, which you should use the sample ID. And then you need to name it. So I'm gonna name it just drainage area DA 17N. And now I'm gonna click run. Okay. So here is our delineated drainage area. So your parents have more knowledge about this study area. So you are the better person to make the judgment if that looks good to you or not. So each color represents each color represents the drainage area corresponding to one single sample point. So for example, if I click on the purple, if I click on the purple or blue, it shows 18. 18 means that's the drainage area corresponding to the sample SS18. If I click this one, yellow, it says the value is 21. So that means that's the drainage area corresponding to the sample SS21. You can tell me if that makes sense. Okay, so up to this point, we have a bunch of, we have a raster layer and color coded, and each color represents the drainage area of one specific sampling location. And then next, we're gonna start to calculate the drainage area. We are gonna start to calculate the percentage of each type of land cover within each of those 11 drainage areas. And the function we're gonna use is tabulate area. So the input raster of feature zone area, so which should be the drainage area layer, which can be a raster or shapefile. So in this case, it's a raster. And the zone field should be the value. And then the input raster should be the land cover we want to know, summarize on. And then class field, so which is basically asking what you want to use, what value you want to use to name the field. So I'm gonna choose land cover. And then you need to rename the output table. I'm gonna give a name is land cover for 17N summary. So again, you see the processing cell size. As I mentioned earlier, the land cover, the resolution of land cover data is 30 meters. So in some case, if one of your sample location, the drainage area, corresponding drainage area is less than, let's say, 900 square meters, you're not gonna have a good result, because in the land cover layer, 900 square meters, that's only one cell. So the derived results from that case will be very inaccurate. So in that case, you need to use some higher resolution data. That's basically the information I want to convey. So okay, after set everything, chose the delineated drainage area raster data, chose the value, and then choose select the land cover, and then we click run. Okay, it's done. So should be at the bottom of the on the left hand side. It's open. So as you can see, each row represents one drainage area, and the number in the value column is corresponding to the sample ID, and then each column represents one type of land cover, and the value in those land cover column represent the area of that specific type of land cover. So to calculate the drainage area, to calculate the percentage of each type of land cover within each drainage area, you just need to sum up all the columns per row, and then use the number in column divided by the total area. You got a percentage. So that's very basic math. I'm not gonna elaborate on that. So if you have any question, you should feel free email me. Oh yeah, by the way, so how to export those values. So normally I would just select all, and then copy, and then I will go to Excel, create a new Excel, just paste. Hold on. Okay, so that's what we got. So again, the column value represents the name of the drainage area, they represent the name of the sample, and then each column, and the value in each column of land cover is the area in map unit of that type of land cover within that specific drainage area. You just need to do some very basic math to get a total percentage. To get a percentage of each land cover within each drainage area or watershed. I hope this video helps you in some way, and let me know if you have any question. I'm gonna send you an email and send you this README text file so that you have something handy. Thank you.